Oh. All right, good evening. Welcome back to Elements of Calculus 2. Today, we are going to start talking a little bit more about Taylor series and why you really want to know them. Let's say, for example, I want to do an indefinite integral. I'll put a definite in there when we get to it, but 1 over the square root of x, e to the x dx. Now, a lot of people have tried to do this by integration by parts, and let's see how that works out for us. So this is x to the negative 1/2. That's a fancy way to write 1 over the square root of x, e to the x. And then what I'm going to do is I'm just going to do my regular my regular integration by parts. Let u equals e to the, or I'm sorry, I don't want that one. I'm going to go ahead and have a x to the negative 1/2, and our du equals negative 1/2 x to the negative 3/2. Okay. So my dv is what's left. So like my dv is e to the x. Okay, we'll say dx. We'll do an integral here. And v, of course, is e to the x. And now we go ahead and do our integration by parts little dance here. And we get x to the negative 1/2 um, e to the x minus plus the integral of 1/2 e to the negative 3/2. Or I'm sorry, no, we have x to the negative 3/2. Sorry about that. Let's go ahead and you go back 1 second here. So this is 1/2 integral um, x to the negative 3/2 e to the x. Okay. And then I'm left with trying to integrate this, which of course I can't because it's a polynomial times an exponential. So we're going to have to go back and we're going to say let u equals, and then you don't want to mix and match what u's and what dv's are. Like once you've chosen one side to be u, you stick with it. Once you've chosen one side to be dv, you stick with it. Okay, if you don't, you end up going around in a circle and usually end up with something ridiculous like, well, something profound like 0 equals 0, which is true, but not very helpful. So you want to stick with one side or the other. You don't want to go back and forth. So we're going to say let u equal x to the negative 3/2 du equals, and here we have negative 3/2 x to the negative 5/2, just taking a derivative, dv equals e to the x, v equals e to the x. So let's go ahead and do this. So we already have an x to the negative 1/2 e to the x, and then we're going to say plus 1/2, and then I'm just going to go ahead and do our little integration by parts stance again. So we're going to have x to the negative 3/2 e to the x minus plus, because we're doing a negative, 3/2 x integral x to the negative 5/2 e to the x. At which point you're going to say, wait a minute, I got to take an integral again because we got a polynomial times an exponential. We're going to do another integration by parts, and so on, and so on, and so on, and so on. And it's never going to end. Okay. We cannot use integration by parts on this thing. Well, you say, well, maybe if we pick the different value, because that happens. Like sometimes we pick the wrong u, the remedy is pick a different u. All right. And that happens to everybody. So don't think to yourself, like, I've never picked the wrong u in my life. Like, trust me, yet. Okay. You haven't picked the wrong u yet. Everybody does. What you do is you pick a different u, or you start hitting it with your algebra hammer for a little bit and see if anything will pop out. But this time we let u equal x to the negative 1/2. Let's turn it around the other way. Let's just say we want to integrate x to the 1/2, x to the negative 1/2, e to the x, and we're going to say fine. Let u equal e to the x, and we're going to say dv equals x to the negative 1/2. All right. So du is simply dx, is simply the derivative of e to the x, and v is equal to, we're going to add 1, so we get x to the 1/2, and we divide by a half, so we end up with 2. So we have 2x to the 1/2 e to the x minus the integral of twice x to the 1/2 e to the x. All right, at which point we've got a polynomial times an exponential. So what we have to do is we have to do integration by parts on this piece again. So we have 2x to the 1/2 e to the x minus 2, and then we're integrating this. So we're going to say let u equal e to the x, du equals e to the x, dv equals x to the 1/2, and v is equal to x to the 3/2, and we're going to divide by 3/2, so we get a 2/3 out here. Okay, so we're going to have our 2 times, and we'll go ahead and do our integration by parts. We have 2/3 x to the 3 halves e to the x, that's this piece, and then minus the integral of 2/3 x to the 3 halves um, e to the x. Okay, at which point you look at this and say, oh joy, we've got another integration by parts here. And again, you're going to go on and on and on and on forever. And this is just going to get bigger and bigger and bigger. And it's never going to go away. This is never going to simplify to anything. And there's even some techniques where we could like swing this over to the other side, but they don't quite match up. So we can't swing this over to the other side and get rid of this integral. It doesn't work. So this is a problem where we simply cannot integrate it using the tools that we have. Okay, in steps, Taylor series, because I know that e to the x is really equal to 1 plus x squared over 2 factorial plus x3 over 3 factorial plus x to the 4 over 4 factorial, we'll say 24, plus dot, dot, dot. So we're going to integrate this, okay, 4 terms out. Okay, so just the terms I have written here keeps going, but we're going to integrate it 4 terms out because we're going to stop it. Okay, and we're going to integrate it between 0 and 1. So here is the plan. Here is the problem. We're going to go from 0 to 1, 1 over the square root of x, e to the x, okay, dx. So there's a couple of things that have to happen first. First off, you may notice that putting in 0 for this, we get 1 over 0, which is bad. So we're going to say, nope, we need a limit, right, as t goes to 0 of the integral of t to 1, because putting 0 in that is going to be, we're going to have some indeterminate forms here. So we need to put the limit in first. And we're going to say this is 1 over the square root of x. And then what we're going to do is we're going to place our e with 1 plus x squared over 2 plus x3 over 6 plus x4 over 24. And we're going to integrate this instead. All right, so let's go ahead and see what that looks like. So we have the limit as t goes to 0, integral from t to 1, and then we're going to have, if I multiply the square root, 1 over the square root of x by each of these terms, okay, we have x to the negative 1/2, okay? That's 1 over square root of x times 1, plus x to the 1/2, right? That's the second one, plus 2 minus 1/2, so 4 halves minus 1/2 is 3 halves. So we have 1/2 x to the 3 halves plus 1/6. And then we're going to say this is 6 halves minus 1/2. So x to the 5 halves plus 1 over 24. X to the 8 halves minus 1/2 is going to be 7 halves. Okay. Now, this is a polynomial. We can integrate a polynomial. This is not a problem. There's no integration by parts. There's nothing. We can just integrate this thing. So why don't we go ahead and do that? Okay, so we'll go ahead and we'll say limit as t goes to 0 from t to 1. Or actually, we're going to integrate. We don't need to write that anymore. So we've integrated. Okay, and let's go ahead and do this as a term by term integration. So I go ahead and add 1 to my negative 1/2. I get x to the 1/2 divided by 1/2, so we get 2 plus, and here we have x to the adding 1, so we're going to add 1 to my 1/2, so we get 3 halves, and there's a 2/3 out in front here. Okay, and then we have plus 1/2, and then we have x to the 5 halves times 2/5, okay, because we're dividing by 5 halves, plus x to the 7 halves. I'm just adding 1 to the 5 halves, and then we get 2/7, and of course we have 1 over 6 out in front plus, and we have 1 over 24. X to the 7 halves plus 1 is going to be 9 halves, and I've got 2 ninths sitting here. Let's clean this up a little bit. So we have the limit as t goes to 0 of x to the 1/2 plus 2x to the 3 halves plus 1/5 x to the 5 halves plus, let's go ahead, this is going to be, if I can read my own writing here. Let's see, this was 1/6, and I think this is 2/7. So let's go ahead and say this is 2 over 42, 6 times 7, x to the 7 halves, and then we have plus, we'll say 2 over whatever 9 times 24 is. We'll go ahead and figure that out for a moment. I think that I did that one over here, and that was 216. Okay, x to the 9 halves. Okay, and we are going from t to 1. Notice that there's no x's in a denominator here. Like this t, I could just directly substitute this integral into, or directly substitute the 0 in for the t, and we're going to get 0, 0, 0, 0, 0. So everything is going to work out. And I picked going to 1 because I didn't want to deal with a lot of arithmetic. If we had to plug any number in here, we could do that. 1's the easiest. So we'll go ahead and do that. What we're going to have, this is going to be 2 plus 2 plus 1/5 plus 2 over 42 plus 2 over 216 minus 0. Okay, let me double check the fact that I have this. Let's see. I've got a 2. I've got a 2 over 3 here. This didn't come down. This is a 2 over 3. Okay, glad I double checked. So that's what we actually have here. Let me pause for just a moment. Actually, you don't need to pause. I'll show you this. We'll go ahead and grab our documents and we'll go off to our calculator to just do that. Bear with me. I'm sorry to do this. I'm sure it's sitting right here. Graphing calculator, graphing calculator, graphing calculator. All right. I'm way back in the day here. So we just have this piece here. So we're going to say this is 2 plus 2 divided by 3. Okay. Plus 1 divided by 5. 1 divided by 5. Now, we can get better accuracy with this thing as we go further and further and further out. That's fine. Divided plus 2 over 42. Okay. Plus 2 over 162 over 216. Okay. And I will just say equals. Okay. 2.9235. Okay. So we have 2.9. We'll write down some numbers here. 2.9235 for and some change. Okay. 2.9354. Okay. So we have that. All right. And that would be my answer for how do you integrate e to the x divided by 1 over the square root of x. The fact that it started at 0 just made like an extra little wrinkle in there because I had to go ahead and deal with the limit. But any two numbers would have been just fine. Again, as long as they are within the domain of my square root of x. So they have to be 0 or bigger because I can't take the square root of a negative number with this. Let me go ahead and show you this as a thought here. So I've got my um, I think I have my Desmos sitting here, and I went through and did this on Desmos, which I believe uses Simpson's method. Remember that from the first test. We'd have to go ahead and graph it, right? And then go ahead and figure out values that we'd have for each of these pieces. But we ended up with 2.9253. And then what did we end up with when we did it this way? And we have 2.925235. So that's pretty close for what we're looking at. Okay, so I don't know which one is better, being Simpson's method or the Taylor series. Someday I might have to do like a whole numerical integration thing, big project, and have students do this. Aren't you glad you're not in that class? To compare, contrast which one is better, which one felt like more work, etc. But we're doing Taylor series in this chapter, so the method that I'm going to say that we have to use for doing this type of integral, when you can't integrate something, we're not going to do Simpson's rule, which I love Simpson's rule, but we're going to try it with Taylor series and do it that way and get an answer. And again, we would get more accuracy for the more terms we went out. It's how far do you want to go out? There's plenty of functions that we just can't integrate. Okay, it just happens. Like there's a lot of things that we simply can't integrate. And who would have thought e to the x over the square root of x would have been one of those functions? Now, you can do some manipulations with this, with its e to the square root of x, square root of x, divided by the square root of x. When you let u equal your square root of x, it actually works out a little bit better. But you'd end up with e to the u squared, which you also can't integrate. So you can play around with this a little bit and try to hammer it into some form that you think you can integrate. But the one that I saw like decides that, okay, well, it looks like e to the u squared, which you also can't integrate. And there's a couple of these functions sitting around that we just knowingly can't integrate. Okay, it just doesn't work. We have to use numerical methods on these things because they don't have nice closed forms. So that's the other reason as to why we want to know a Taylor series is because if you don't know how to integrate a function, or if we don't know how to integrate something, can we replace it by its Taylor series and integrate it that way? Now, you do have to pay attention to your radius of convergence for this problem because e to the x equals 1 plus x squared over 2 factorial plus dot dot dot. This has a radius of convergence from negative infinity to positive infinity. It works for all real numbers. Not every Taylor series is going to do that, okay? But e to the x is a really safe one to be able to use for this thing. So we can go ahead and use that as an approximation for e to the x and integrate it term by term by term. So this is a very, very powerful method which allows you to integrate functions that you may not have had a lot of experience with, like all of the trig functions, where you don't really need to know how to handle the trig functions. If you can replace them with their Taylor series, that's often a really good approximation for the integral that you're trying to deal with. Okay, and it also saves you like having to graph it and deal with Simpson's rule for it as well. So we could do that. But that's why you want to do this. Thank you very much for watching the video and take care. Goodbye.